Hello everybody, this is Nicolas Zabaras. This is Statistical Computing and Machine Learning, and we continue our lectures on regression models. So today we will discuss about the evidence approximation that we have seen earlier when we discussed about hierarchical Bayes models and empirical Bayes approximations. So we will see those applied to regression models today. So let's see what the topics to be covered today. So we will review some of the basic things we have seen about the evidence approximation, and we will apply those directly to our standard regression problem. We will discuss about calculation of the marginal likelihood, and then try to maximize the marginal likelihood with respect to the hyperparameters in the prior, and in the process we will see some geometric interpretation and somehow discuss how the model is able to learn an effective number of regression parameters for a given data set. Alright, so the goals for the lecture today will be to review the evidence approximation and then apply it to our regression problems, and discuss about how a Bayesian formalism and this empirical Bayes model can produce for us the effective number of parameters for the regression model. All right, so let me remind you the setting that we discussed earlier on hierarchical Bayes models. So what you see here is the equation for the marginal likelihood. So this is our likelihood model. W are the regression parameters. We're working everywhere with model M. This is the prior in W, and you notice this prior has hyperparameter theta, and this is the prior on the hyperparameter theta. Now, if you want to be fully Bayes, what you need to do is you need to compute this integral after you put this particular prior of W given eta, and then you have a prior on eta. So you will need to be able to work with a joint prior on W and eta. Now, when we discuss about the evidence approximation, we saw that a good way to approach this that does not require the full integration of in the space of the hyperparameters would be to estimate a point estimate, eta hat, let's say, that maximizes the marginal likelihood. So the idea is there, instead of pre-selecting what the hyperparameters eta are going to be, select them as a point estimate, but that point estimate has to be very sensible. It has to be the point estimate that maximizes the marginal likelihood. And that's what we will discuss today in the context of regression models. So before I do this, I want to go rapidly through some review of model comparisons and calculations of the model evidence, and then we will directly apply all of these concepts to our regression model. Okay, so let me go directly to what we have seen up to now. We have a number of models that I call them here MI. Each model has a prior. And if you use Bayes' rule, the posterior over models is the prior times the likelihood, and this likelihood is a marginal likelihood. It's you notice there is no, the parameters W don't appear anywhere, so they have been integrated out. So that's the marginal likelihood. And we discuss using these posteriors in model selection and model comparison, and one of the ways that we introduced model comparison was through the Bayes factors, and the Bayes factors were nothing else but basically the ratio of the marginal likelihoods for two models. So if you want to compare model I and J, you can take the ratio of these marginal likelihoods, and you can see from the two equations the ratio of the posteriors is really proportional to the Bayes factor times the ratio of the priors. Okay, if you are going to produce posterior over models, the question then is, how do you actually do predictions? And what I mean with predictions, so given your training data set D, you want to predict for a given test data point X, you want to predict what the response or target T is. And a good way to do this is using this equation that you see here that may look very complicated. Actually, it is not. First, notice that on the right hand side, the different probabilities are conditioned on the model MI, and I'm summing on the model I. On the right hand side, there is no model MI. All right, so that's the overall predictive distribution. First, how do you get this equation, right? So you can actually use the sum rule of probability. So you can write this as summation over the model psi of the joint of T and MI, and then use the product rule to come up with this equation. So when you look at this equation, that's a model averaging equation, because effectively what it tells you to find the overall predictive distribution, take the predictive distribution for each model and weight this with the posterior of every model. All right, so this is how you're going to do predictions if somehow you manage to compute these posterior probabilities of every model. So that's model averaging. Now, in principle, nobody wants to do model averaging because there's lots of computational effort. So actually what you can do, you can select the model that has the maximum posterior probability, and then for that model use the predictive distribution that you see here. So you're going to use basically a point estimate for the predictive distribution for the best model. All right. So effectively, if you're going to do predictions using the best model, that's the idea of model selection. Otherwise, if you're going to use the equation that you see on the top, that is the Bayesian way of doing model averaging. All right, so let me remind you a little bit about how we compute the model evidence. So we're going to take a model MI, all right? And what you see here is the normalization factor that appears in the Bayes rule when you write down the posterior of W as being the likelihood times the prior divided by the normalizing factor. This is the normalizing factor. That's the marginal likelihood, okay? So what you have here is the likelihood for model MI times the prior, and then the parameters integrated out. And again, if you want to see the Bayes rule from where this equation at the top comes, literally what we have in the first equation is the denominator in the Bayes rule for the posterior of Wi under model MI. Now, one way that I want you to actually look and interpret this marginal likelihood is the following. You sample some parameters Wi from the prior model that corresponds to your model MI, all right? And then you are looking for the probability of generating data D for these parameters with your likelihood model for model MI, okay? So this is the way that you need to interpret this marginal likelihood, is the probability of generating data D by randomly sampling from the prior of your model and using your likelihood model. Okay, so these are again our two equations. This is the posterior over models. This is the marginal likelihood that I had before. And we discuss about this very nice graphical representation that gives you on the vertical axis the marginal likelihood for different models. The horizontal axis are data that have been ordering complexity, and these are different models of different complexity as well. So M1 was a very simple model, M2 was an intermediate complexity model, and M3 was a high complexity model. Okay, and remember the way that we generate for a given data set this marginal likelihood is we're looking for random samples from the prior to actually generate this data through the likelihood model for this particular model. So If you take model M1 and let's say a particular data set D0, so model M1 is a very simple model. So it can generate very few data sets that look very similar. And the probability of generating this data set is very high. Okay, if you take another model of intermediate complexity, you can generate a little bit more data sets. Okay, but with a lower probability, because at the end of the day, if you take all the probabilities of the data that you can generate, the sum of those probabilities has to be equal to 1. So now, because your probability is spread over more data sets, this probability has to be reduced, and that's why this red line is below the blue line. And similarly for the more complex model M3. So from this schematic, you can see that the Bayesian approach to model selection, effectively for this data set D0, it selects a model of some intermediate complexity, and effectively this is consistent with the Occam's razor principle that we have discussed in an earlier lecture that says prefer simple than complex explanations to your data set. Okay, so effectively by maximizing the marginal likelihood, you are trying to do the best possible fit through your likelihood model to your data set, but at the same time, and we will see this explicitly in a few slides, you are penalizing yourself when it comes to complexity. You don't want very complex models, because you can see again from the discussion that we had here, the probability of generating a particular data D from a very complex model is decreasing. All right. So it is a model of intermediate complexity that eventually it is the optimal model for generating this data D0. Okay, let's do a little bit of trivial calculation, and this is a much more trivial calculation than the Laplace approximation that we have seen in an earlier lecture, but qualitatively basically will allow us to have the same discussion on the form of the marginal likelihood that we have seen with the Laplace approximation. So what I'm going to do is I'm going to use the posterior being the likelihood times the prior divided by the marginal likelihood. So I rearrange, and I have for a particular model the marginal likelihood being the likelihood times the prior divided by my posterior. And then what I'm going to do is I'm going to evaluate all of this around the map estimate. Okay, so I am going to assume basically that my posterior is sharp around the map estimate. So everywhere where I have W, I'm going to use W map. So here's the prior, and from the schematic that I have here, the prior, because it integrates to 1, is 1 over delta W prior, where delta W prior is the support, where the prior is non-zero. And similarly, using a sharp posterior and with a spread of delta W posterior that is much less than delta W prior, because you remember the more data you get, the more narrow your posterior becomes. So this posterior becomes 1 over delta W posterior. And of course here I'm going to use my likelihood model evaluated at the map estimate. Now keep in mind that delta W posterior divided by delta W prior is less than 1. So if I take logs, my marginal likelihood can be written like this. And notice that this is again negative, all right? So this is a negative. And the way that I evaluated this equation, I only assumed one parameter W, okay, with this schematic, but you can actually generalize this for for m parameters. And what I have in this equation here, I'm assuming that I have the same delta W posterior divided by delta W prior for all the parameters W, and I have m of those. So my marginal likelihood is written by the log of my likelihood evaluated at W map plus m times log of delta W posterior divided by delta W prior. Now, if you look carefully here, right, so if you want to maximize the marginal likelihood, effectively what you need to do is, try to maximize the likelihood. And we already know the more complex the model, the better fit you do to your data set and the higher the likelihood. So you can keep going forever on this. But then at the same time, you need to minimize the complexity of the model defined by this m. And I remind you, you need to minimize because this ratio here, this log is, this parenthesis is less than 1, so the log is less than 0. So this is a negative term. So you need to penalize the complexity when you maximize the marginal likelihood. So you have two competing terms. One is the likelihood term that likes to be as high as possible, and the other one is the complexity of the model that likes to be as minimum as possible. So the interplay between those two gives you the optimal complexity of the model, and that's what we have seen under the Occam razors principle that we discuss in this lecture and in earlier lectures as well. Okay, so so this is again exactly the the same picture that we had before, and I remind you, this is very essential. The way that I want you to think of this marginal likelihood is as the probability of generating data through your likelihood model with parameters W randomly sampled through your prior model. All right, this is how we have introduced and interpret this marginal likelihood. So what you see again in this model, in this picture, you can see three models of increasing complexity. So you can think this being in the context of regression, a linear polynomial, this is quadratic, and this is cubic. And if you look at a particular data set, the optimal model complexity, let's say it is quadratic polynomials, and that's what this pictorial in this particular case shows. Okay, so the idea here again is that if you look at this particular data set D0, you realize it cannot be generated by this simple model M1. All right. It can be generated by model M3, but model M3, the very complex model, assigns very low probability to the data sets that it can generate. So if your objective is to maximize the marginal likelihood, then this intermediate complexity model, it is the optimal model for your particular problem. All right. We can, if you want, we can look at this optimal model selection with a different eye. And what I want to show you is that a Bayesian model in an average, all right, will select the correct model. Let me go through directly the equation so this can make sense. You remember the KL distance between two distributions, right? Measures how close two distributions are. So let me actually try to take these distributions of the data D corresponding to the exact model, all right? That's model M1, and then to some other model M2. So if I use the definition of the KL distance, and remember the KL distance is always greater or equal to 0. So if you look at this equation, you can see that in an average with respect to the exact, marginal likelihood, right? This probability here that corresponds to the exact model. So in average with respect to this distribution, minimizing the KL distance, points to the model M1 being the correct model, because the only way for this to be greater or equal to 0 is for this ratio to actually be greater or equal to 1, which implies that the model M1 has to be the correct model. All right, so the idea here is that in an average, the Bayesian setting will favor the correct model using this KL distance. Okay, so you can see this sort of as an alternative way of approaching this model comparison and model selection problem by using the KL distance. Okay, now we had revisited, if you remember, this calculation of the marginal likelihood by using the Laplace approximation. And for those who forgot, I am going to remind you that the Laplace approximation, what it does is it looks to a Gaussian approximation of the posterior of your parameters. So if you have, let's say, some parameters in your model, and for whatever reason I call these parameters in this slide theta, okay, and I'm working with model M, so you can maybe you don't have to pay any attention to the subscript M. So I am looking at the posterior, and the Laplace approximation is nothing else but fitting a Gaussian model in the mode. All right, so this Gaussian will be centered in the mode of your posterior, okay, and it will be in such a way that it has the same curvature as the exact posterior. So a good way to actually derive the Laplace approximation, and I'm not going to do it, right? I'm going to highlight it. If you take the log posterior and you do a Taylor series expansion, and you keep up to quadratic terms, and you do your Taylor series expansion around the map estimate, so at the theta point estimate that maximizes the posterior, then the only thing you're going to get is you're going to get a constant term and this quadratic term where a is minus the second derivative of the log posterior at the map estimate. And you're not going to get any linear terms because, you know, the gradient of the log posterior at the map estimate by definition is 0, right? That's where the log posterior is maximized. So the linear term is not there. And what you have is the quadratic term. And the constant term basically serves as a normalization factor for the Laplace approximation, for this Gaussian distribution that you see in the equation here in the bottom. So this approximation is extremely important, is used in many applications. If you somehow assume that your posterior is unimodal, you can fit a Gaussian around the mode, and this Gaussian is known as the Laplace approximation or a Gaussian approximation of your posterior. Now, why I mention this Laplace approximation? Because we have seen that can be used to get a much more accurate calculation, an approximation, if you like, of the marginal likelihood. So the way we derive this is by writing our marginal likelihood. All right, I am writing it as the ratio of the joint probability of the parameters and the data set for my model. So think of this as being the likelihood times the prior. That's what it is. The likelihood times the prior divided by the posterior. So if you take logs on both sides, all right, and you write this joint distribution of theta and d as the log of the likelihood and the log of the prior, compute it at theta map. This is what I have. And then on the denominator, you're going to have minus the log of the posterior. And for that, what we're going to do is we're going to use the Laplace approximation. But I am doing this evaluation of the log marginal, approximating all the parameters theta at the map value. Okay? And remember, at the map value, if I can go back in this equation, when you take logs of this posterior, you're going to get the logs of the normalizing terms, but this quadratic in the exponential will disappear because you're going to have theta map minus theta map, so that will give you 0, and that's what you get here. Okay, so we get this nice, wonderful expression for the an equation that gives me an approximation of the log of the marginal likelihood in terms of the likelihood and the prior model. And then we had this determinant of A that involves minus the second derivatives of the log of the posterior computed at the map estimate. Okay, so let's do the following thing, right? I'm going to use this approximation, but now I am going to take a limit of this approximation when the number of my data goes to infinity. So I'm going to take n to go to infinity. Now remember that A involves second derivatives of the log posterior, which is likelihood times the prior, and remember the likelihood increases with the number of the data points n. So it is a good approximation to assume that as n grows, this matrix A grows as n times A0 for some fixed A0. Okay? So this matrix A that you get by taking second derivatives of the log posterior, as n goes to infinity, increases as n times some fixed matrix. So if you use this approximation inside log of the determinant of A, effectively what you're going to get is log of n to a power d, where d is the dimensionality of the problem, how many parameters I have in my model, times the determinant of A0, and you can write this d log of n plus log of A0, so as n goes to infinity, this becomes d log of n, okay? And by the way, pay attention when you take log of the determinant of n times A0, this determinant is n to a power d times the determinant of A0. You don't move the scalar outside the determinant, right? You're going to get n to a power d, where d is the dimensionality of your parameters. All right, so what we have is we have a nice approximation for log of the determinant of A. Now, when you have a lot of data, this term will become insignificant with respect to this term, all right? So, in many ways you can drop this term, because here you have d log of n, for n a very big number. So effectively you have a nice approximation as n going to infinity of the marginal likelihood being the log of your likelihood evaluated at theta map minus d over 2 log of n. So if you cannot really compute exactly the marginal likelihood, you can use this so-called Bayesian information criterion that you see here. And this Bayesian information criterion approximates the log of the marginal likelihood as the log of the likelihood evaluated at theta map minus d over 2 log of n. And now you can see again this interplay between maximizing the likelihood and then minimizing the complexity of the model that has to do with how many effective parameters you have here. So this is the number of parameters, but in reality, in a Bayesian setting, d is the number of effective parameters that you can compute from your data. And we will see this in the particular example we're going to do for regression models later on in the lecture today. So this is, again, this schematics, as I showed you before, for computing as an optimal model, a model of some intermediate complexity that somehow maximizes the likelihood, but somehow keeps the complexity of the model as small as possible. So we're going to have to compute this type of marginal likelihoods, log marginal likelihoods in our calculations in the lecture today, because this is how we're going to be allowed to compute the not only the the number of, let's say, how many parameters we're going to have or how many basis function we're going to have in the model, but also use this to optimize the hyperparameters that use in the prior of our model. So let's start moving in this direction, and we're going to go directly back to our standard regression problem. And so let me remind you what we have, right? So this is a model that has a likelihood. This is the likelihood here. This is my regression function y of x comma w, all right? So that's my likelihood, and I take the likelihood has a precision beta, okay? So we're going to compute today in the lecture with this evidence approximation what beta is. So that's my likelihood model. And then I had a posterior, and I remind you the posterior. So given my training data, and I'm only showing you the target training values, I don't show you the input bold X here to make the notation simple. So my posterior for W, it was given by this nice expression where Mn and Sn inverse were the mean and the precision for this posterior, and we computed these results in the previous lecture. So what you see in this equation is the full predicted distribution. So if you need that some new X, some unbold X, to compute what the target value T is given some training data, what you need to do is you need to take your likelihood times the posterior of all your parameters, and the posterior here involves the posterior of W given the hyperparameters alpha and beta. Alpha is the hyperparameter coming in the prior model for W, right? That was the precision in our prior model. And then you're going to need to have a prior model on the parameters alpha and beta. And we said that in a fully Bayesian setting, you're going to need to do this integration in W, in alpha and beta, but we don't really want to do this because it's going to be very complicated. So we don't want in the lecture today to have to compute this posterior. So this posterior, if I can write it, I can approximate, so this is what I have here, right? So we're not going to compute this posterior. What we're going to do instead, we're going to fix alpha and beta in some point estimates. And you can think those point estimates corresponding to, the map estimate of alpha and beta. And this is what I have here, all right? So if I take alpha and beta with a hat to be the map estimate to maximize this posterior of alpha and beta given my training data T, then I can write my predicted distribution as follows. This is my likelihood for a given beta hat, and this is now my posterior of W for given alpha hat and beta hat. Okay, in some sense this is what we did in the previous lecture, but in the previous lecture, if you remember, we a priori selected alpha and beta. Today in the lecture, we're going to select this alpha hat and beta hat in a way that is consistent with hierarchical Bayes and this evidence approximation. So we're going to select alpha hat and beta hat by maximizing the marginal likelihood. Now, where is the marginal likelihood comes from? So let me point you to this equation. This equation gives you the posterior of alpha and beta, and I'm writing this as the marginal likelihood times the prior. So if you take the joint prior on alpha and beta to be, a uniform, uninformed prior, so equal to 1, then the posterior on alpha and beta, it is actually the same as the marginal likelihood, all right, is the same as the marginal likelihood written down as a function of alpha and beta. And I call this marginal likelihood because there is no W here, because W has been integrated out. So actually, if I can see the equation, here is my marginal likelihood. All right. To be able to evaluate this, the way I'm going to do it is I am going to use my likelihood model for some beta and my prior for some alpha, and integrate all the parameters W out. I want you to think of this equation again as the denominator in the Bayes rule when you compute the posterior of W. So what do you have in the denominator? You have the likelihood for a given beta, right, times the prior for a given alpha. And that's the marginal likelihood. And effectively what we need to do in the lecture today, we need to find this alpha hat and beta hat in a way that maximizes this marginal likelihood. Some reminders: this is my prior, right? Alpha is the precision of the prior. I am using here, to be consistent with the notation from Bishop's textbook, I am using M as the total numbers of W's that I have in my model. Now the likelihood is a Gaussian model, and I have n data points. So this error function here that you have in the exponential obviously has to be the square error of your regression function at the training inputs from the target values in your training data set T. Okay, so this is what I have. So effectively, if I can rewrite my marginal likelihood, this E of W is given by beta over 2 times this square error of the error of my regression function in approximating in coming close to my target values T, and then this term W transpose W times alpha over 2 comes from my prior, that is a Gaussian with mean 0 and precision alpha. Okay, so that's a nice equation for the marginal likelihood, and literally our objective for the next 5 to 10 slides is to do nothing else but basically maximize this marginal likelihood with respect to the parameters alpha and beta. So you notice alpha and beta also come inside this energy, so we're going to have to compute, I call it energy or error function, right? So you're going to have to be careful when you do optimization of alpha and beta to account for whatever terms you do this coming in your model. Now this function that you see here is quadratic in W, right? This is a quadratic term, this is a quadratic term. So effectively, if you use a Taylor series expansion, it will terminate at the quadratic terms, right? So you're going to have a constant term, and by the way, I'm doing the Taylor series expansion around the posterior mean of W. Okay, so I'm going to have E evaluated at the posterior mean of W, that we call it Mn, and then I'm going to have a linear term that I'm going to come back to it, and a quadratic term where obviously A is nothing else but the second derivatives of E of W with respect to W. Okay, now there's no linear term, and the reason there is no linear term, as you can expect, is that if you take, how do you define the map estimate, right? It is your point estimate that maximizes the posterior. So the derivative of the log, the derivative basically of this thing at the map estimate is equal to 0. Okay, so I am not going to put any first term because it has disappeared. So the expression that you see on this slide is actually an exact expression. It's not an approximation. So let me now tell you what we're going to do, right? So what we're going to do, I give you here all the expressions, by the way, for what A turns to be, what E of Mn is. E of Mn will be taking this and putting W equal to Mn, and the posterior mean is given by this nice expression. And I told you alpha is the second derivatives of E of W with respect to W. And you can, once you do the differentiation, this is what it comes out. So now what I'm going to do is I'm going to take this, plug it in the equation on the top, and see if I can do the integration exactly. And you can guess you can do the integration exactly because this is a constant term, so you can pull this outside the integration, and this is a quadratic term, and with the exponential here, when you integrate W out, it will give you nothing else but the normalization factor of a Gaussian, okay, of a multivariate Gaussian. So, and here's the answer, right? So if you put things on the exponential, what you get is you get the normalization factor of a Gaussian, and I remind you the dimensionality of W that I take here is M. So this is what I have, and if you put everything together in your marginal likelihood, this is the expression that you get, and on the bottom I also give you the log of the marginal likelihood, and effectively we have, for our particular problem, we have a closed form solution for the log of the marginal likelihood. So if you look carefully, we have a term that involves M, right? That's the complexity of the model. This has to do with a number of my data sets, right? But involves beta as well. Then we have E of Mn, and remember this contains if I can go back, E of Mn, okay, is given here, right? That's E of Mn, okay. Nmn again is the mode of the posterior of W, and then we have the log of the determinant of A, and then another term that involves N. So now we have to go through this not very complicated but very insightful calculation of taking derivatives of this with respect to alpha and beta and trying to find the hyperparameters that we will use in our evidence approximation or the empirical Bayes method that is the focus of the lecture today. Okay, so before I do the calculation, right, let me just give you what you can do once you have this nice analytical expression for the evidence. So let's say that somehow you have computed the optimal alpha and beta, and what you see here, they are not really the optimal, but let's say you computed them, and then you can ask yourself, can I find the optimal order of the polynomial to use on my regression function? And the answer is yes. And what is your criterion? The optimal will be the one that maximizes your marginal likelihood. So when you compute your marginal likelihood for different orders M, it turns out that M equal to 5, right? So a fourth order degree polynomial, it will be the optimal polynomial that fits the particular data set that we review. Actually, this is the same data set, the sinusoidal data set that we saw in our previous lecture. Now, it's interesting how this nice plot of the marginal likelihood, all right, as a function of the order of the number of parameters, okay, it actually relates with these curves that we saw when we discussed about least squares estimates with no regularization a few lectures ago. And what this plot on the right shows here is the training data set as the order of the polynomial increases. And remember, for a polynomial of, for m equal to 9, we perfectly fit all our training data sets. This is for 10 training data points. But notice for testing, so if you test the algorithm for the computed W from least squares for a data set that you have not seen before, when you put m equal to 9, the test error blows up because of the overfitting that we discussed, in 1 or 2 lectures ago. So in our case, m equal 4 is the optimal solution, and when you look at those plots here, you know that anything in between m equal to 3 to 8 gives you the same error, so you could have selected any of those values, but the evidence approximation tells you that m is equal to 4. So one scalar quantity is enough to actually compute the optimal number of basis functions in your model, or the order of the polynomial, if you like, for this particular data set. Okay, so let's go and do the optimization of the marginal likelihood that we derived. And to do the optimization, we're going to have to do a little bit of algebra. So the first thing I'm going to do is, and I'm going to follow the notation directly from Bishop's textbook. And so what I'm going to do is I'm going to use the eigenvalue problem corresponding to the matrix beta, phi transpose phi, and I'm going to call the eigenvectors ui and the eigenvalues lambda I. Okay? First, remember capital phi is the design matrix, and the reason I put that beta there is because simply it makes the algebra to look a little bit simpler. Okay, other books like in Murphy's book, there is no beta there, so you have to be careful when you compare results from different sources. But here we're going to use the eigenvalue problem for beta, theta transpose phi. Okay, now remember the matrix we care in our problem is that matrix A. This is what comes in the evidence approximation. So this A is alpha times I plus beta phi transpose phi. So obviously if the eigenvalues of beta phi transpose phi are lambda I, and you shift this matrix by the matrix alpha times the identity matrix, then the eigenvalues will shift by alpha plus lambda I. So the eigenvalues of A is they are alpha plus lambda I. Okay. Now, why is this important? Because if you remember in my log marginal likelihood, there was a log of the determinant of A. So a good way to compute the log of a determinant, and in particular taking derivatives of this, is to express this matrix A using its eigen decomposition. And that's what I have done on the equation that you see on the bottom. So if you think A being represented in its eigen functions ui, A will become a diagonal matrix with values in the diagonal equal to the eigenvalues, which are lambda I plus alpha. So the determinant of A will become the product of these lambda I plus alpha terms, and then the derivatives with respect to alpha will be 1 over lambda I plus alpha. Okay? Now, a little bit of explanation here. You notice that when I do this, this differentiation with respect to alpha, I keep the eigenvalues lambda I constant, even though, so, I mean, I'm looking at this expression, right? There is, so alpha, all right, is the eigenvalues of alpha are alpha plus lambda I. Now, lambda I comes from the design matrix that involves your inputs only, all right? There is a beta there. So there is really, lambda I is constant here in the derivation. So this gradient is 1 over lambda I plus alpha summation on I, okay? For a moment I thought that there was another approximation there, but really what we have is summation of 1 over lambda I plus alpha. Okay, now let's look further in the calculations here, okay? And so let's see what we have here, okay? So there is an alpha on the first term, so I am going to get m over 2 alpha when I take derivatives. I look at Mn, there is 1/2 of Mn transpose Mn, okay? But now notice there is, there is, if you pay close attention, right? Mn depends on the matrix A, and matrix A depends on alpha. So what I'm going to do is I'm going to keep this matrix A fixed, and I'm not going to take derivatives of Mn with respect to alpha, because as you will see shortly, I'm going to be doing an iterative process where for a fixed Mn I'm going to be recomputing what alpha is, and then I'm going to be reevaluating Mn and keep iterating. So for now, when you take derivatives of this with respect to alpha, I only account for this term 1/2 Mn transpose Mn, and I don't touch the dependence of Mn on alpha that comes through this matrix A. And so similarly here, there is another dependence that we derived on alpha, and I have 1/2 summation on I of 1 over lambda I plus alpha. So if I rearrange, I get this nice equation that you see on the bottom that says that alpha is equal to gamma divided by Mn transpose Mn. What is gamma? I define gamma to be the summation of lambda I divided by lambda I plus alpha. So I want you to remember this gamma because it's going to come to play an important role in interpreting this type of calculations. So gamma is the summation of lambda I divided by lambda I plus alpha. And you can see this equation is not directly useful unless you start doing iterations, because gamma itself depends on alpha, and then as we saw, Mn depends on the matrix A that depends on alpha. So you need to really do an iterative implicit calculation where you choose an alpha. If you choose an alpha, you have a matrix A. If you have A, you have an Mn. If you have, you have the eigenvalues lambda I. So for that chosen alpha, you can compute alpha. You can compute gamma. So on the right hand side, you know what gamma is, you know what Mn is, so you can recalculate alpha. And once you have a new alpha, you can come back, compute a new Mn and a new gamma, and recompute alpha and keep iterating until convergence. And this is what I am showing you with all the equations for this implicit calculation of alpha. So this calculation actually does work, okay? But you have to do iterations, so when you take these gradients with respect to alpha, you don't get an explicit equation for the update of alpha. Now, I can do the same thing for beta, okay? And I remind you, for beta, things are a little bit more interesting, because these eigenvalues lambda I, you notice they depend on beta, because the way that I define this eigenvalue problem is such that it is the eigenvalue problem. So lambda I is the eigenvalues of beta phi transpose phi. Okay? You can actually see that lambda I, it is proportional to beta. So you can agree with me that the derivative of lambda I with respect to beta is lambda I over beta. Okay, because of this proportionality, and then that log of the determinant of A that we had before, I can take derivatives with respect to beta, so this will be 1 over lambda I plus alpha times the derivative of lambda I with respect to beta, which is nothing else but lambda I divided by beta, and this whole summation, we call it gamma. So there is this term here. When you differentiate with respect to beta, you get a gamma over beta. Now, if you differentiate with respect to beta the other terms, you're going to have a contribution from here, right? You're going to have a contribution from here, where I'm only going to account for this sum of squares term, while keeping Mn constant, exactly as we did before, because we're going to do iterations. And this is what you get. Take derivatives with respect to beta equal to 0, rearrange, and this is the final result. So it turns out that the precision in your likelihood, all right, the precision in your likelihood is given by 1 over so this is the variance, actually 1 over the precision, right? The variance is 1 over n minus gamma, and the summation of this square error of between your targets and the answer that you get at each training point using your regression function, okay? Now, what I want you to keep attention on this slide is, and I'm going to mention this now, even though it may come up in a slide or two, I want you to remember this form of this equation and how it relates with the maximum likelihood estimate for the variance. So I remind you that when you do the MLE estimate for the regression model, right, that's the MLE estimate for a Gaussian, what you get is you get the sample variance. So you get 1 over n, the summation of these square errors. Now what we get is 1 over n minus gamma. Now, if you remember, for the Gaussian, the sample variance is a biased estimator of the true variance. And the way that you correct that bias in the MLE estimate is to use 1 over n minus 1 times these square errors. Okay? 1 over n minus 1. And the statisticians explain this subtraction from n of 1 by saying 1 degree of freedom has been taken to calculate the mean. And in this case, the mean in a regression model involves these parameters W, right? And the MLE estimates for the W. So you can immediately see that maybe this parameter gamma plays the role of the effective parameters that the model can compute from data. So gamma is the effective number of parameters. So because you already can compute gamma number of parameters, to get an unbiased estimator for the variance, the Bayesian model directly takes care of that by subtracting gamma from n in this estimate for the variance that you see in the equation on the bottom. So the Bayesian methodology effectively correctly accounts for for this bias aspect of the MLE, and it corrects it by computing an effective number of parameters. Okay, and then the estimate that you see on the bottom, it is avoids all these issues of overfitting and everything else we discuss in the context of the maximum likelihood estimates. We will see this shortly, and I'm going to give you some geometric interpretation of gamma, but I wanted you to, at this point, to relate this equation with the unbiased estimator for the variance for the multivariate Gaussian, or for the MLE estimate that we did in the last lecture. We have 1 over n minus 1. Here we have 1 over n minus gamma. So gamma needs to play the role of the effective parameters in the model. So what I'm going to do now is I'm going to try to discuss a little bit geometrically and with some algebra how does gamma comes to have this interpretation as the effective number of parameters in the model. And I'm going to do two rather equivalent sort of analysis of the meaning of gamma by using the notation both from Kevin Murphy's machine learning book and also from Bishop's book. And the two methodologies you will see, they may look different, but actually they are one and the same thing. They only differ by some normalization constants that I will identify for you. So if you can follow one or both of these derivations, then you're all set. So let's see exactly I'm going to bypass this slide, right? We don't really need it. So let me go directly to, maybe we need to jump to slide 31. Let's go directly to this slide. Okay, so what I'm going to do is I'm going to take the singular value decomposition of my design matrix phi. Okay, so I'm writing phi as the orthogonal matrix U times this matrix with the singular values times another orthogonal matrix V transpose. So the mean of my posterior for W, it is given by this expression that we have seen this analytically derived in an earlier lecture, and I gave you expressions in many slides before. So if you plug in phi to be U as V transpose, and use the orthogonalities of u and v, you get this nice expression for Mn, where lambda, all right, where lambda comes to be the ratio of alpha over beta. So this is our regularization parameters we have seen, right? So that's the ratio of the precision of the prior divided by the precision in your likelihood model, okay? So I call this lambda, okay? That's our regularization parameter. All right, now, somewhere in an earlier lecture, I have given you a geometric interpretation of the least squares prediction, all right? And the least squares prediction is we have this target values t of my training data. So what we do is we project those, all right? We take the projection of those in the eigenvectors uj. These are the columns of u. And then the least squares estimate is given by this expression that you see here. Okay? The least squares estimate is nothing else but take a projection in the columns of u, all right? And this is it, right? This is my least squares estimate. uj times uj transpose t. Now, the regularization estimate for the solution, which corresponds to the Reed's least squares estimate, is nothing else but phi times the posterior mean of my parameters. So when you substitute phi with your singular value decomposition and you substitute Mn by this expression that I give you here, and you just follow some trivial algebra, you can immediately see that the Reed's estimate is nothing else but the following. Take your target vector t of your training data, project it in each of the columns of the matrix U, scale it by sigma j squared divided by sigma j squared plus lambda, and of course in every axis this is projections in the different axes uj. These are the columns of U. That's your Reed's estimate. And what is sigma j squared? Sigma j here are the singular values of the matrix phi. Okay, sigma j are the singular values of the matrix phi. Now, for those who have seen singular value decomposition before, the eigenvalues of phi transpose phi are literally sigma j squared. Okay, sigma j squared. Now, if you want, since we used before the eigenvalues and eigenvectors of beta times phi transpose phi, so you can see beta times sigma j squared in this slide is really nothing else but the lambda j that I used a few slides ago. Okay, so this is again from Murphy's notation. If you want to discover the lambda j, and we will do this in the next slide, if you want to discover this lambda j from the eigen decomposition of beta phi transpose phi, the only thing you have to do is set beta times sigma j squared equal to lambda j. Okay? All right. So if you look at the Reed's regularized estimate, this is the Reed's solution. You notice that you have this scaling factor sigma j squared over sigma j squared plus lambda. So I am actually going to call the effective degrees of freedom to be this summation of sigma j squared divided by sigma j squared plus lambda. Okay? This is, by the way, with this substitution that you see here, this is identical with the gamma parameter that we saw before. Okay? Identical. All right? So if you put sigma j squared to be lambda j over beta, and you put lambda to be a over beta, you get the identical expression that I had before for the gamma parameter. But notice now what happens. If sigma in a particular direction sigma j, because here what I have done is I decompose my Reed's solution to different components in the directions of the eigenvectors defined by the columns of U. So if sigma j squared in a particular direction, sigma j, is much less than lambda, then this term becomes 0. Okay, so if sigma j squared is much bigger than lambda, then this becomes equal to 1. Or you can actually see this alternatively, and if lambda goes to 0, all right, and lambda goes to 0 means no regularization, then the effective number of parameters is m, which we expect. And if lambda goes to infinity, then you can see that the effective number of this becomes 0, the effective number of parameters becomes 0. So you can see that somehow that gamma parameter that we had before, or this summation that you see here, effectively defines the effective number of the parameters that can be identified by the data set that you have in your training set. Now, I mentioned here, if I have a small sigma j, right, that this term will be very small, right? So effectively what I am telling you, looking at this decomposition of the Ridge solution in the directions of these eigenvectors uj, the contribution, the component of the Ridge solution that you get in the j direction, if sigma j is very small, is 0. And that means that, you know, that those sigma j's don't contribute to the Ridge estimate, okay? And effectively, the parameters, you know, wj in those directions are 0, right? Because the parameters, if you look, the coefficients of my solution in the directions j where sigma j is very small, they are literally 0, okay? So that means that the estimate for the parameters w in those directions is equal to 0. So effectively the data cannot compute those parameters, and those parameters are set to 0 by the prior. Okay? And it turns out, if you take you know, a flat prior, a uniform prior, that these directions where sigma j is very small correspond to the directions where you have the maximum posterior variance for w. So the directions where you have the highest uncertainty for w, those are the directions where the parameter w is set to 0 by the prior model. Okay? The rest of the directions become effective directions, and they contribute to this, the degrees of freedom that I have here, the effective dimensionality of your problem. Okay, I'm going to sort of repeat these calculations now once more without doing the singular value decomposition of phi, and I'm going to start directly from the eigenexpansion of beta theta transpose phi that we had before, but effectively we're going to get the same results, and I want to show you these results graphically. So what you see on this extremely messy slide, what I have done is I have aligned my likelihood model with the directions of these eigenvectors u1 and u2, all right? And I remind you in the notation that we used before, u1 and u2 are basically the eigenvectors of phi transpose phi. So what you see here is one contour of the likelihood aligned, all right? These contours are aligned with the axis u1 and u2. So this is my parameter w1 and w2, and this axis are in the directions of u1 and u2. Now notice this is my MLE estimate, all right? And this is my prior estimate that has a prior mean equal to 0. So if I take my general expression for the posterior mean given on the top, and I'm expressing it actually in terms of the MLE estimate, okay? There is nothing fancy here, all right? I am, you know, I actually, if you remember the MLE estimate, what it is phi transpose phi inverse times phi transpose t, Okay, so I'm substituting here phi transpose T as phi transpose phi WMLE, so I can get an equation that relates the mode of the posterior for W in terms of the MLE estimate for W. So what I'm going to do is I'm going to use the the eigen decomposition of beta phi transpose phi that I had in my previous slide using Bishop's notation. So UI are the eigenvectors, lambda I the eigenvalues of beta phi transpose phi, and when you plug in this in the posterior mean estimate, what you can do is you can write the posterior mean in the directions of UI, where here inside the parentheses I have these projections. Lambda I and lambda I plus alpha is what we have seen before, and WI MLE is nothing else but the projection of the MLE estimate in the direction UI. All right? Again, take the eigen expansion of phi transpose phi, plug it in here, you will immediately get Mn given like this, and I call this Wi MLE, and I have these are the coefficients of the projections of Mn in the direction UI. Now let's look in the direction of U1. Okay, you notice in the direction of U1, lambda 1 is small, and if lambda 1 is small, you can see that the component that I get for the posterior mean in the direction U1 is then 0. And you know what that means is that effectively this component is set by the prior equal to 0. Okay, is set by the prior equal to 0. So this is the MLE estimate, this is the map estimate, and you can appreciate, at least in this geometric representation, that the W1 component of the map estimate is very small. Okay, and again, I am doing this looking at the direction of U1, where lambda 1 is small. So this is the direction in which the likelihood function is insensitive to the parameter value, and the parameter value is being set to a very small number by the prior, and that small number here, I'm taking it to be very close to 0. So when I say this is set to 0, I mean to a very small number. Now, if you take the direction 2, all right, lambda 2 is high, so you get actually this estimate here, and that's the W2 component of the map estimate, all right, that is significant. Okay, so the direction W2 in this particular model is an effective dimension, and the model is able to compute this projection of of my this is the posterior mean in the direction of the eigenvector U2. Okay, so effectively now you can get an understanding why the summation of lambda I divided by lambda I plus alpha summed over all the eigenvalues is the effective dimensionality, and you can appreciate that this parameter gamma varies between 0 and m. Okay, so effectively what we have is this parameter gamma does nothing else but measures the effective dimensionality of the problem. Effectively, it tells us how many parameters the model can identify from the particular data set. The rest of the parameters are set to very small values, let's say 0, by the prior of your particular model. Okay, now it turns out with this number of effective parameters that we can relate this idea with what I mentioned before with the unbiased nature of the estimate, and I reminded you that in the MLE estimate for the variance, the unbiased estimate is 1 over n minus 1. So 1 degree of freedom is taken to define the mean. In our case, gamma degrees of freedom are taken to define the gamma effective parameters in our model. The rest of the parameters are set to 0. So effectively, the Bayesian formulation automatically accounts for the biased nature of the MLE and corrects for it. All right, and it corrects for it. And this is what is being discussed on this slide. In relation to the MLE estimates that we have seen many lectures ago. So the model has m parameters, right? That's what we started. But the effective number of parameters identified by the Bayesian method is equal to gamma. So the other remaining parameters m minus gamma are going to be set to 0 or something very small, near 0, by the prior model. Let me, I believe we missed a few slides with some results. Let me go back, if I can, 2 slides, okay? And I'm going to give you some pictures that show this evidence approximation in action. And the first pictures I'm going to show you are some results coming from Kevin Murphy's PMTK toolbox. So here is the first plot that shows the log evidence versus log of alpha for a particular data set. So you're going to have to click the program and see what is the data set being used. But you can see this log evidence has a very nice, sharp, easy to identify maximum when you plot it versus log of alpha. All right, so this is what you identify as our estimate alpha hat in the evidence approximation. And here is another plot that gives me the log evidence in terms of log of alpha and log of beta. And in the first plot, what is actually shown is the negative log marginal likelihood. So obviously here you are minimizing the negative log marginal likelihood in terms of log of beta. But what I want you to note is the location where this negative log marginal likelihood is minimized. It turns out to be about the same location as the place where the mean square error in a cross-validation setting is minimized on a test data set. Okay, so that's very nice, right? So you do get basically very close to what we have seen with using cross-validation. And on the picture on the right, again, we see the log evidence for this particular problem versus log of alpha. So you can imagine in this type of optimization problems, you may want to fix alpha, do the optimization on beta, then fix beta, do the optimization on alpha until convergence, or try to do the optimization for alpha and beta simultaneously and see if that process is actually going to work. So let me, I'm going to give you a few more examples. So we, again, we discussed the geometric aspect of this problem and the effective number of parameters identified by the data. So let me move to give you a few more plots. All right. So if you remember in our iterative process for alpha, we had that alpha was gamma over mn transpose mn. So you can, if you plot here alpha times mn transpose mn, all right, that's this curve. You plot this for different values of alpha, and you plot gamma. This is this curve. This will be basically the point that they intersect, and this will give you the right value alpha hat for your model. And again, this is a similar plot. This is for our sinusoidal data set for m equal to 10 with 9 Gaussian basis functions, okay? And you see the point where the marginal log likelihood becomes maximum. It's about the same point where the test mean square error is minimized, okay? And so that seems to be in agreement with what we have seen earlier for selecting with cross-validation hyperparameters to the model. Now, here is another plot. So in this plot, what we do is we vary the parameter alpha from 0 to infinity to cause this number of effective parameters to vary between 0 and m, all right? And then I plot the mean estimates for the parameter w versus gamma. And you can see how the effective number of parameters varies basically between 0 and m, all right, as we vary alpha. Okay, so this is, again, we're plotting the mean of the posteriors of w, all right, computed with different alphas corresponding to different gammas, and you can see how the as gamma varies, how the number of parameters goes from all w's being 0 to actually all w's being non-zero. Okay, now if it happens that you have a lot of data set in your problem, right, you anticipate that in this case the the number of effective effective parameters in your problem will be equal to m. Okay, so the idea here is, you remember we computed the eigenvalues lambda I of the matrix beta times phi transpose phi, and phi transpose phi, it's a sum over data points. All right, so if you have a lot of data points, then lambda I becomes bigger and bigger and bigger. So basically all dimensions become very important. So gamma becomes equal to m. And it turns out in that case, when you look at the re-estimation equations for alpha and beta, you don't have to do any iterations. And actually you don't have to, so if you go and you put gamma equal to m, okay, you get this nice equation. And here we're supposed to have 1 over n minus gamma, but n is much bigger than m. So we have 1 over n given like this. And you notice in this particular case, you don't really need to compute the eigenvalues lambda I of phi transpose phi, all right, in your re-estimation equations. And alpha and beta are readily available by the two equations that you see on this slide. Okay, so that's the end of the lecture today. And what I want to do on the next short regression lecture will be to do a few more examples with the evidence approximation, and also introduce some conjugate priors for the regression parameters w and the variance or precision lambda or sigma, sigma square or lambda respectively, and see some uninformed limits of those priors, in particularly discuss about what's called the Zellner prior that is very common in regression models. So I am going to stop here, and we will follow up in a day with our next and final lecture on regression models. Until then, see you later. Bye.